This video will work through example 2. Example 2 is quite similar to example 1. The changes are that the water level on the front side is lowered to level -3 instead of -1 before, and further the variable load on the ground surface is moved to act on the ground 1.5 meters away from the retaining structure, which means that it will affect the retaining structure in level -1.0. All other parameters are the same. The exercise is still to determine the necessary length, maximum moment, and anchor force in the sheet pile wall in the long-term state, under the assumption that the wall will fail with one yielding. Because of the many similarities to example 1, we will start by opening this example. So go to the SPOOKS program, press File and open example 1. Then save this as example 2, and then we can start making the changes. The calculation method is the same, the wall is also the same, the stratification is changed, but let's wait with that. The water levels is changed. On the front side we need to change the water level from -1 to -3. And then we have the loads, and they are also changed. The load is still of the magnitude 22.5 kilonewtons per square meter. However, the ZR value is changed because the load will affect the wall at level -1.0. So this value here has to be changed to -1.0 and press OK. We can change the project data from example 1 to example 2. And then we need to change the stratification. We change the water levels, which means if we look here at the sketch, we will have a flow from the back side underneath the sheet pile wall towards the front side. That means that we need to introduce a gradient. The gradient is calculated based on Bent-Hansen's formulas, and a small Excel spreadsheet has been made to calculate the gradients. We need to enter up here the driving depth, and this is the result from example 1. Then we can calculate H1 and H2, which are heights of the sheet pile wall, and HW is the difference between the water levels on the back and front side respectively. Then we can calculate the gradient I1, which is the gradient on the back side, and I2, which is the gradient on the front side. Let's enter these two gradients into the program. On the back side it should be 0.13, on the front side 0.25. And then remember that the sign convention is that the gradient should be positive for a downwards flow, and the downwards flow occurs on the back side, therefore it should be positive here. On the front side, however, we have an upwards flow, and we need a minus in front of the gradient. Press OK. Now we have made the changes that we need, and we can calculate the project. The results shows that we have a significantly larger driving depth here, which will again change the gradients on the wall. So we need to calculate the gradients once again. We need to enter over in the Excel spreadsheet a new value for the driving depth. It's now calculated to -9.4. This gives a significantly change in the gradients, and these gradients needs to be entered in the stratification tab. On the back side the gradients are changed to 0.10, and on the front side they're changed to -0.16. Press OK and recalculate the project. The new results gives a slightly shorter wall. We go back to the Excel spreadsheet, enter the new value for the driving depth, and we see slightly changed gradients. Again, go back to SPOOKS, enter the stratification tab to put in the new changes in the gradients. Press OK and calculate the project once again. The results shows now only a slightly larger wall. However, entering this in the Excel spreadsheet gives no changes as long as we only calculate with 2 decimals, and that is what SPOOKS is able to do in this matter. This means that the iteration for the gradient is now finished, and the results that we see here are the final results, including the flow around the sheet pile wall. We found a maximum anchor force, a maximum moment, and a driving depth. These are the values that we need to see further for the design of the sheet pile wall.